Welcome, everyone. We're delighted to see all of you here for today's distinguished Vinberg Distinguished Lecture. Our speaker is David Fisher. He's the Ruth Halls Distinguished Professor of Mathematics at Indiana University in Bloomington. He received his bachelor's at Columbia and PhD at the University of Chicago in '99 under Bob Zimmer. He was a Gibbs instructor at Yale and then was at CUNY at the Graduate Center for a time before joining Indiana, starting there as an assistant professor in 2005, and he's been there since. His research interests are in rigidity and geometry and dynamics, is what we're going to hear about somewhat today. Analytic and geometric group theory, ergodic theory, Lie groups and their discrete subgroups and generalizations. He has many awards and honors, National Science Foundation postdoctoral fellowship, NSF career grant. He was a fellow at the Radcliffe Institute at Harvard. He was a fellow of the American Mathematical Society. He's a Simons Foundation fellow. He gave a seminar Bourbaki lecture on the Zimmer program. He's a Miller professor at Berkeley. He was a Simons professor at MSRI, and he'll be an ICM speaker in one way or another this summer. So we're delighted to have him here. And David will tell us about arithmeticity, superrigidity, and totally geodesic manifolds. Please take it away, David.
All right, thanks. Thank you for the very gracious introduction and for the invitation. It's a pleasure to be here, and particularly a pleasure to be here given that I have recently, in the last few years, I've become intrigued by Vinberg's work. And so what I'm going to start with is a bit of, first I need to define some words. So, in this talk, G will always be a simple Lie group. The key players in this talk will be where G is either SLNR or SON1, which everyone here probably knows is the isometry group of the hyperbolic n space, and also SUN1, which is the isometry group of the complex hyperbolic n space. And then gamma in G is lattice. This is, i.e. discrete, and volume of G mod gamma finite. And yes, you can think of gamma, if you want to think of gamma from a algebraic perspective, you should think of SLNZ sitting in SLNR. Or if you want to think of it as from a geometric perspective, you could just think of it as the fundamental group of a compact hyperbolic manifold. And whatever your preference is or your choice is, do one of those. And sorry, my iPad froze a little. And there's sort of one key definition I want to make before I start telling you a little bit about history. And that is that a lattice gamma in G is arithmetic if there exists a number field K and ring of integers O of K such that, and here I'm just going to put in parentheses up to conjugation. Everything in this talk is pretty much up to conjugation. Gamma intersect with this G of O of K has finite index in gamma and G of O of K. And this notion of having finite index, the intersection having finite index, is called commensurable. So I'm hiding a second definition in my direct definition. I will use the word commensurable for now on for this property of having two groups where their intersection is finite index in both of them. And there's some sort of remark I have to make here is that this is not the original definition of arithmetic lattice, and it's a slightly tricky definition. I'm hiding some complications by stating things this way. I'll say a little bit more about the history of that later, because I've learned some things recently that I find fascinating about the history. And I'm going to start the history very early with the theorem of Selberg from 1960, which really I think is the origin of this particular subject in some sense. That if here he takes gamma and S ln R, he insists n is greater than or equal to 3, gamma a lattice. And then he says, then there exists a number field K such that, again, up to conjugation, gamma is contained in G of K. So we don't quite get into the ring of integers, but we at least get into sort of the rational points of the number field. And I sort of forgot to say, which I always say in these talks, is if you don't like number fields and you don't like rings of integers, just think Q and Z throughout my talk, and you don't lose very much. So Selberg proved this. And then shortly afterwards, this was extended to all G except SL2R by an incredible list of authors. I give you some of the names. You know, Calabi was involved, Bay was involved, Raghunathan was involved. It's just sort of a flurry of activity by incredibly famous mathematicians who extended this result. And something that's often attributed to Selberg as a conjecture, but if you actually read the paper, it's very strange and it doesn't say what people generally claim it says. It's in the same paper from 1960. Selberg says, well, if G is not SL2R, and he really says this when people claim he says something much stronger than this, then perhaps gamma should be contained in G of O of K. It's really the statement in Selberg's paper, and it's, you know, it's not stated, it's stated in line. It's not in a conjecture environment. It's just, you know, he says maybe if your group isn't SL2R, then maybe this is true.
So David, the first thing is the rigidity, right? The Selberg rigidity.
Yes.
There's no deformations of before you get to arithmeticity.
Right. So maybe some other history that's not in my notes, but the lad is, you know, this is proven in all cases, first by Selberg and then by these other people, by showing gamma has no, you know, let's just say deformations in this context in G. And, you know, to make that precise, I have to say too many things that I don't want to emphasize in this talk. So I'm not going to say exactly what no deformations means, because it has to be no non-trivial deformations, because you can always just conjugate the lattice around. You know, everything in the talk is up to conjugation. So anything that's just a conjugate, that's the same thing. And another, you know, maybe that's historical remark one on this conjecture. And remark two is somehow that, no, Mostow rigidity was proven to understand this better. And, you know, what that means is up to, you know, the reader or the listener. I certainly had conversations with Dan about this where he insisted on this. And there's even a remark in the introduction to Mostow's book on Mostow rigidity, where he says the reason he proved Mostow rigidity was he didn't like it, the proof that there are no deformations that these other authors came up with, that these folks came up with, depended on cohomology computations. And Dan, you know, actually share this sense with him. Cohomology computations end up like sort of not feeling transparent and intuitive. You reduce something to cohomology computation, and then you do some cohomology computation, and at the end of the day, you know your theorem, but you don't know that you feel in your bones why it's true. And so Dan really proved Mostow rigidity because he wanted to know in his bones why this result about lattices having entries in algebraic numbers was true. He wanted a better feeling for that. And you can deduce that from Mostow rigidity using results of Weil and results of Selberg. And I think people forget this because there are all kinds of other reasons in the modern world that we care about Mostow rigidity, but this is why Mostow cared about Mostow rigidity. And the next sort of chapter in the history here is.
But already having entries in a number field means there can't be deformations, right? So Selberg sort of saw the first hints of rigidity.
Yeah, I would say Selberg saw the first hints of rigidity. And the other thing that I learned not from Mostow, but from Margulis, secondhand from Mostow, is that if you look at Selberg's actual proof, Selberg's proof is not a cohomology computation. Very few people read it. And if you look at it, there is some sort of, Mostow rigidity is proved by, looking at this boundary map at infinity. Selberg is very much looking at high powers of group elements. So there's something asymptotic in Selberg's proof where, somehow, if, maybe in the right point of view of history, Selberg, had the right idea, and this detour through cohomology computations was a detour. And, then the other work of Mostow and Margulis and their followers on rigidity is all much more following closer to Selberg's original ideas. I think that's true. The next step in this, which, I have to emphasize particularly because I'm giving a Vinberg lecture, is that the next actual revelation in this story was the work of Makarov and Vinberg that said there exist non-arithmetic reflection groups which are lattices in SO31, SO41, and SO51. I should say this maybe sometime around 1965 or 67, somewhere in that range, depending on when they told the difference between when they told their friends and when they published their papers. And actually, at least some of Vinberg's, I don't know about Makarov's, I wasn't able to read that paper in time, are not integral. They define not only the arithmeticity possibility, but they don't satisfy Selberg's sort of conjecture or speculation. They really are genuinely not what was expected, even if you give Selberg credit for asking a more modest question. There's some sort of strange interaction between my iPad and the screen that's causing me to double take. But
so you mean Selberg didn't say higher rank?
Selberg really said not SL2R, and I think somehow this is a historically important fact that Selberg said not SL2R, and it actually informs my opinion of some questions I'm going to ask later. The interesting thing is, you tell this to a modern mathematician and they say, no, come on, Selberg knew there were non-arithmetic lattices in SL2C. And I really think if you read his paper, the answer is then on the day he wrote his paper, if he knew that, he forgot, right? Like, Selberg was a very guarded guy, and you don't know what he actually knew, but the paper very clearly does not think SL2C is going to be like SL2R. And I think this one is somewhere between 1966 and 68. Piatetsky-Shapiro goes and modifies the conjecture. If G has higher rank, then gamma in G lattice implies gamma arithmetic. And I think for the purposes of this talk, just to avoid saying technical things, if G is S ln R, higher rank is n greater than or equal to 3. You want a definition in general. There are 6 different ways of saying it. I'm going to skip that for today because it's not going to be crucial for most of my talk.
And I guess all SON1s are rank 1.
All SON1s are rank 1. All SUN1s are rank 1. And then this conjecture didn't really actually last that long. I find it surprising in retrospect because it's in my universe, it's such a big deal that Margulis proved this. And again, there's some collection of dates one can give to this that I'm not so sure are precise. Margulis then, proves this. He proves that if G simple R rank G greater than or equal to 2, then gamma in G lattice implies gamma arithmetic. And, the conjecture between when it was first formulated in some sense by Selberg, when it was clarified by Piatetsky-Shapiro, and when it was proven, that's, 15 years. It's generally viewed as a monument in mathematics, but it was, it wasn't like it was an old conjecture when he proved it. It was a new conjecture. Conjectures don't have to be old to be important. Somehow another thing that gets lost in history, except among experts, is Margulis actually proved this twice. He first proved it for non-uniform lattices. And this is probably less spectacular an achievement, but I'll just say here that this uses homogeneous dynamics. There are ideas in this proof of arithmeticity that are used every day by everyone working in homogeneous dynamics to prove everything they prove. It's ideas about non-divergence of unipotent orbits that come from him proving arithmeticity. And apparently what he tells me is Piatetsky-Shapiro had claimed he knew how to prove this non-divergence, but did not. So in the non-uniform case, it was kind of following an outline that Piatetsky-Shapiro seemed to know, and led to, pretty much the birth of homogeneous dynamics, I think. For uniform lattices, he proved what's called superrigidity to prove this, and this roughly classifies all finite dimensional representations and I'll say something more about that later when I'm actually using a superrigidity theorem. I'll tell you something more about superrigidity. I just want to tell you, for sort of in this first half, I want to tell you a bit more of history and speculate a bit about future history. And really, the bit more of history doesn't last that much longer in some sense. There, we hit a big lacuna at some point, but in '82, Thurston's work gives just tons of, I'll be informal, tons of non-arithmetic lattices in SO31. Tons of is very informal, but certainly he produces a lot of them. And what I don't know in a strong sense, right? Thurston's interest was not in arithmetic. Thurston sort of changed our point of view on hyperbolic geometry, and he was not interested in arithmetic very much. And so while Thurston produced all these lattices, I think it isn't till later work of Alan Reed and other people close to him in the 90s or late 80s that we actually knew which of these lattices were arithmetic or not. Thurston was working on topology problems, not geometry and arithmetic problems. And following this, starting in about 1980 and going to about 1986, Mostow and Deline Mostow found non-arithmetic lattices in SU21, where they found 11, and SU31, where they found 1. And now, due to work of many more people, we have 22 of these and 2 of those. So, this is a very strange world where, And it's also true that Thurston, this is hard to date because the paper appeared very recently, and I don't know when it was actually written anymore, and around, maybe 88 to 90, reinterpreted exactly the 12 due to Deline-Mostow. Here I'm correcting something I've said wrong in print. I've claimed that all 24 of the lattices we know now can be constructed by various different methods, and I've made some slightly false claims about that. There's a lot of mystery left in this world. I'll say some things about that later. In 88, Gromov and Piatetsky-Shapiro using hybrid constructions build non-arithmetic lattices in SON1 for all n. And it's important here that, like, unlike this situation where there are finitely many, they build infinitely many commensurability classes. So they're just tons. They don't actually say this in the paper, that they're building infinitely many commensurability classes. This is somehow more a modern point of view on the question to be concerned about that. And so, they do build infinitely many commensurability classes, but they don't claim to. I have no idea how. On my screen,
thing, I'm sick of this fucking bottle shit. Quit fucking kicking tops off of bottles, you goofy.
Sorry about this, David. We released the Zoom link, and we might have to remove some people. So
yeah, I looked up and I saw this red scribble on my notes on the screen, which I don't know how to
let
get
me
rid
figure out a way to turn that off.
And then we got the battleship.
I'm pretty sure you just gotta like reshare your screen or something.
No,
Hello.
yeah, I think we're not going to let anybody else in from the waiting room.
I think that would be clever. We'll just keep going. The red scribble we don't have to worry about. Oh no, we do have to worry about. Okay, I will reshare my screen. I suspect that is the right answer. There we go. We're back. We have no red scribble. All right. So, Gromov and Piatetsky-Shapiro gave this great construction where they construct infinitely many in all dimensions. And then something happened that, again, I don't think we appreciate in the right way in the modern world, which is Corlett, and very quickly after him, Gromov-Shane sort of completed the picture. And this is all happening in around 92 or published in 92. All lattices in SPN1 and F4-20 are arithmetic. And the important thing here is that, these are, maybe this is a remark, these are rank 1. And after this, and all but SON1 and SUN1. So, there really are, they're these collections of lattices in various infinite families, and collections of Lie groups in various infinite families, and somehow these rank 1 groups don't behave like the other rank 1 groups. The quaternionic, this one corresponds to quaternionic hyperbolic space. This one corresponds to the exotic Cayley hyperbolic plane, and somehow their lattices act like they're higher rank in this way and in some other ways. And the one historical remark I think gets lost in our modern point of view is that this was really not expected. Nobody thought this was going to happen. Maybe people around Yao and Su had more of an inkling that something like this could be true, but it's not at all clear. I mean, it sort of came out of the blue, and it sort of, broke a paradigm. The paradigm Piasecki-Shapiro was predicting was that there was one set of phenomena for rank 1 groups and one set of phenomena for higher rank groups, and this says no, it doesn't quite break on the line you want it to break on. I have 2 more bits of history I want to state before stating some of my own results, and then probably running out of the first half of time.
So is it more like property T is the dividing factor rather than rank 1?
It could be, but like the fact that you get arithmeticity and property T at the same time, there isn't, there are 3 things that happen for SPM1 and F4 minus 20 in my mind. There's property T, arithmeticity, and superrigidity, which is where arithmeticity comes from. And then there's just quasi-isometric rigidity too. And all of those things are shared by higher rank groups and these particular rank 1 groups. And there isn't sort of good coherent explanations of any of that. It's, it's sort of like, these are the phenomena we know are shared by these collections of objects, but it's not like there's some explanation that makes it sort of satisfying that that's what happened. At least to my mind. So just because I emphasize integrality, I feel I have to finish emphasizing integrality. And God, I hope I spelled these names right because I spelled them wrong before. Maybe my handwriting will cover for me. So work of Agel and Belopetetsky-Thompson building on Agel's work shows that there are lattices in SON1 for all n that are not integral. They don't live in the integral points in the sense that Selberg conjectured. And then there's the counterpoint theorem to that, which I just love this contrast of a theorem of Esnault and Gruschunig that's very recent from 2018 that says all lattices in SUN1 are integral. This result I also want to advertise because somehow people don't know this result not well enough. It's quite a striking result. Part of why people in this world don't know this result is because they don't mention SUN1 in their paper. They're talking about representations of fundamental groups of certain projective and quasi-projective varieties, and so they don't talk about what we would all probably consider the key examples while giving their proofs and theorems. Yeah, it's I like this because somehow it's a further instance that this intuition that we all, or at least that I was sort of raised with, that rank 1 and higher rank are different, and SUN1 is just like real complex hyperbolic space is like real hyperbolic space, but just harder. Well, no, it's not. It has really different phenomena that we finally begin to understand. It's not an accident that we
But are they integral? It means that they are sitting in integer points, right? Or
I mean, you have to be a little bit careful to be correct, right? They're conjugate to sit up to conjugation. They're at finite index sitting in critical in integral points.
Well, what Belopetetsky, Thompson, and Agel construction, they, as I remember, they did quasi-arithmetic, so it means that they sit in rational points, but not.
Yes. Yeah, absolutely. What Agel and Belopetetsky-Thompson do is they really show that, I mean, how I always think about this is there's some p-adic completion in which they show that in that p-adic completion, the action on the building doesn't fix a point. That takes care of both conjugacy and finite index.
Mm-hmm.
And Esnault and Gruschunig prove exactly the opposite. They prove that if you take any p-adic valuation, then the action on the building has a fixed point. And so there really is it's just very different. You can't there are a bunch of speculations in the literature and privately of ways that you might try and take the Gromov-Piasecki-Shapiro construction and adapt it to do something in SUN1 instead of SON1. And the Agel and Belopetetsky-Thompson construction is an adaptation of Gromov-Piasecki-Shapiro, And this is like, to me, a big warning sign about trying to do this, anything analogous in SUN1, because you're trying, if you could do something that was the GPS construction in complex hyperbolic geometry, well, then you would be able to disprove the S0-Groshonig theorem at the end of the day. And so you better not try to do that. So, this is just, from some point of view, I think that this result, the contrast between these two results are important and indicate to me that there's this entire line of research that people have been pursuing about trying to adapt these hybrid constructions to complex hyperbolic geometry. And this tells me, yeah, that shouldn't work. It's not a proof that it doesn't work, but it indicates that something is wrong and it probably should not work. I want to, yeah, I was worried about this when I wrote my history down, that I was going to spend too much time on history. But I do want to emphasize, before I talk about the work I'm here to talk about, I want to emphasize two questions, which I like and are really the motivation I had for starting to think about hyperbolic geometry in a serious way in the last 5 or 6 years. The biggest question in the field is, perhaps, and the field of studying lattices and arithmeticity is, do there exist non-arithmetic lattices in SUN1 for n greater than or equal to 4? And if you read the literature and the speculations in the literature, and even, like there's a recent survey by Kapovich where he states that there do exist as a conjecture. And I do think that, if you did a poll of mathematicians, most people believe these exist. I'm tempted to believe that they don't. And that may just be me being ornery and contrary, but it also somehow relates to the following question, which is really where I started my journey into hyperbolic geometry. And it says, if n is greater than or equal to 4, I'm going to state this geometrically because it's easier. Does there exist a finite volume non-arithmetic hyperbolic n manifold that does not contain a totally geodesic? Maybe it wasn't actually easier to state this geometrically. Submanifold of codimension 1, i.e. a lattice gamma in SON1 that intersects no conjugate of SO m-1, 1. And why is this a question? So the only ways we know of building hyperbolic manifolds in dimension at least 4 is to either do Gromov-Piatetsky-Shapiro constructions and their variants, all of which involve cutting and pasting along exactly these totally geodesic codimension 1 submanifolds, or we can do reflection group constructions a la Vinberg, all of which, because you're doing a reflection, there's the mirror for the reflection that automatically gives you a codimension 1 submanifold that's totally geodesic. And I will admit that when I first came to this question, I thought the answer was probably, yes, of course there are such things. And I tried for a while to build them. With Lafont, Miller, and Stover, we can build some examples that aren't yet in the literature because we haven't written them down, because we wanted them to give the negative answer to this question, and they don't actually do that. They do something else. And they're not as interesting as I want them to be, and it's a lot of work to write them down. And I just think this is very reasonable conjecture to which, there should question to which there should be a yes or no answer. And it really is a question about, does hyperbolic geometry in dimension 4 and above look like hyperbolic geometry in dimension 3? Because, you know, in dimension 3, answer is yes. There, there are lots of examples. If you ask someone like Alan Reed or Matthew Stover to give you an example, they'll turn on the computer and give you 12 and 15 minutes. It's not a hard problem there. And there is, I won't write this on the screen because I'm behind schedule, but there's also a speculation in the original Gromov-Piatetsky-Shapiro paper where they ask if there's some sort of question where they ask if all hyperbolic manifolds in high enough dimension might be built from what they call subarithmetic pieces, where, the very first question you have to ask to make sense of their question is, if the answer to this question turns out to be no, and every non-arithmetic manifold contains these walls, then the Gromov-Piatetsky-Shapiro question kind of makes sense and is a question. And if the answer is yes, then it's absurd. It's ridiculous. It doesn't mean anything. You have to make sense of their question, you have to start cutting your manifold into pieces. I also like the fact that maybe it's just a coincidence based on what we know and don't know at this moment in history, but the fact that the number 4 occurs in both of these questions, that could be an accident or it could mean something, right? I really started thinking about these things because, about real hyperbolic geometry, because complex hyperbolic geometry seemed just way too hard. And I was interested in the first question and eventually stumbled across the second question and, sort of then want to understand what is going on with, these things in general. And the theorem we were able to prove about this, that maybe I will state and then talk more about after a break. This is with Botter, myself, Miller, and Stover. And I guess the version I'm going to state, you can call this a theorem from 19 or a theorem from 20 or something like that. And I'll state the most general version of it. So G now can be SON1 or SUN1. And it's only interesting for these in the way, I'll make it clear in the way I state it, that it's only interesting for these. So gamma in G a lattice. And then, M, which is G mod gamma mod K, is a real or complex hyperbolic manifold. And the conclusion we get is that if gamma is not arithmetic, then M contains finitely many maximal totally geodesic submanifolds and just to be clear, I should say maybe that these are closed. I'm not interested in the non-closed totally geodesic planes that are always there. I'm interested in the closed ones that aren't always there. And I should remember to specify of dimension greater than or equal to 2, because totally geodesic manifolds of dimension 1 are geodesics, and all negatively curved manifolds have infinitely many closed geodesics. We're not interested in that case. We're interested in higher dimensional things. A few remarks on this. One is maximal means what it has to mean, is not contained in another proper totally geodesic manifold. If you don't like that definition, you can just think maximal you can stick to the real hyperbolic case and stick to the case of codimension 1. And to me, emotionally, you lose very little. That was the key case I was most interested in. And somehow this also is an attempt to make sense of this Piotrowski-Shapiro-Gromov question, because what it tells you in that case is if I have a hyperbolic manifold that's not arithmetic, and it has one totally geodesic submanifold that could cut the manifold into pieces, well, it has at most finitely many. And at that point, you have sort of a semi-canonical way to cut your manifold into pieces. That makes the Gromov-Piotrowski-Shapiro question potentially make sense. If you didn't have something like this, the question wouldn't actually make sense. Maybe remark 2 should be the brief history of work on this question, which I like just because it's mildly ridiculous. In 2018, with Lafont, Miller, and Stover, we proved this for the GPS manifolds. It's a little strange. We prove it for the GPS manifolds, but not for the variants constructed by Agel and Belopatetsky and Thompson. So really the GPS manifolds. But you should also see sort of there's a crucial observation in our paper that also appears at exactly the same time in a paper of Benoit and O. I do not know which one of my team and their team actually observed this first. It was at essentially the same time. And they don't realize its relevance to this problem, even though at least Heo did know about this problem, but they did something else with it. In 2019, we do the, Bowder, Fisher, Miller, Stover, do the real hyperbolic case. And at the same time, Margulis and Mohammadi in just dimension 3, give another proof, which I used to say I was confident enough in Margulis that his proof would extend and cover the same cases as my proof. And he and I have talked about it a lot since then. And their proof is different enough that it really does not work in higher dimensions without significant additional ingredients that none of us know how to prove. So, and again, I think they beat us to the archive by 3 or 4 weeks, but the paper they archived is about half as long as the paper they're eventually publishing. So maybe they were taking some slight shortcuts to beat us to the archive. And then in 2020, we finally got the complex hyperbolic case, which makes it, the total theorem. But this was also, almost simultaneously proved, slightly later, but close to simultaneously. Baldi and Olmo proved most of our theorem, but not all of it. Only for complex, totally geodesic submanifolds. And I found this experience quite striking just because I've never actually had competition in my mathematical life till this 3-year period. I would prove theorems and you'd worry that someone else was working on the same theorem, so you'd rush to get your version written and you'd be very nervous. And it never actually was real. It was something that was a fairy tale people told about competition that never had occurred in my life. And then I started working on this subject that I thought was, not too fashionable. So I didn't have to worry about competition. And somehow I had to worry a lot about competition. And then I guess the last thing maybe I should say is that my third remark should be that for the real hyperbolic case, this answers questions of McMullen and Reed. I think Kurt McMullen had only asked this about hyperbolic 3 manifolds. Depending on whether you depend on what Alan Reed had put in print or what he told his graduate students over beer, he stated this fairly generally, maybe even in the complex hyperbolic case. But all those stories are stories of what happened over beer, several beers in. So I don't know. I don't know quite how generally Alan knew that this phenomenon was going to take place, but he seemed to have known quite a bit about it. And they both asked it as questions rather than made it as conjectures. I don't know that anyone was certain of what was going to happen. I guess I'm going to say maybe we should stop here. I am behind schedule, but I think we should stop here and take the 10-minute break if we're going to take it, and then come back.
That sounds great. So why don't we unmute and thank David for the first half. It's a beautiful discussion. Thank you.
Yeah, thank you.
Okay. I clearly underestimated how much time it was going to take me to say some things. So I'm going to skip some things that are normally in the talk when I talk about this. And I'll just point you to the fact that there are many other Zoom recordings of me talking about related work. And the thing I'm skipping is there's a connection to some work of Margulis and Alan Reed on commensurators and their connections to arithmeticity and their connections to totally geodesic manifolds that really provide a lot of historical motivation for our theorem. So this theorem that maybe I should emphasize again, because I'm just going to talk about some ideas in its proof for the rest of the lecture, is it says that if I have a real or complex hyperbolic manifold and it's not arithmetic, then it contains only finitely many maximal closed totally geodesic submanifolds of dimension at least 2. That's what the theorem on the screen says. And then you can read this in the converse, right? And what we actually prove is or the contrapositive. We prove the contrapositive, which says if there are infinitely many totally geodesic closed submanifolds of dimension at least 2, then gamma is arithmetic. And so we actually prove that, even though I actually think this version of the question is probably the one that one wants. If this has many future applications, what one wants is this, and not the converse, or the contrapositive. Sorry, but this is but we prove the other. And to do this, I just sort of call this towards proofs. And I will have to tell you a bunch of things about Margulis's work, and if you learn things about his work and not mine, that's okay. So the sort of key observation that goes back to things I said earlier is that to prove arithmeticity, prove something called superrigidity. And so most of what I'm going to tell you about is how you prove superrigidity. And I'm not going to tell you about how superrigidity applies arithmeticity, because that really is Margulis's work. And it's actually kind of funny. He talks to me about this intermittently, about the fact that he's clearly not quite sure that the proof that the fact that superrigidity implies arithmeticity was original, because it's actually pretty easy. But he's constantly telling me that this or that other famous person in the world has told him, yeah, that seemed to have been new at the time. And I think why it was new is because no one expected superrigidity, so no one had tried to prove that it implied arithmeticity. You don't make an observation about something that sounds like fantasy. So let's just state Margulis's version of this, or a version of Margulis's version of this, and then I'll state a version of our version of it, and then we'll talk about the proofs and how they compare some ingredients that are new in our proof. So if I have gamma, oh wait, let's just start with G, higher rank, gamma in G, a lattice. G is a higher rank simple Lie group, and if you want to think just SL3R, I'm happy with that. And we're going to look at some homomorphism rho from gamma to H, which has Zariski dense and unbounded image. I guess I'm putting this in the wrong order. For it to have Zariski dense image, H should be, say, a simple algebraic group over a local field K. I should say here, the fact that I can let this local field be p-adic instead of real or complex is very important for the implication to arithmeticity. But if you want to ignore it for now, I'm kind of okay with that. That's, maybe it's too much for people who don't know that theory to try and absorb it in a seminar lecture. And the conclusion of this is both surprising and simple. It says that then rho extends to G. So, the takeaway should be that the sum reasonable and necessary assumptions on my homomorphism from gamma into any other algebraic group, the homomorphism extends. And there are more precise things one can say and more generality, but I mean, this is a true and precise statement, but there are stronger things one can say in greater generality. But this is sort of the statement he needs for arithmeticity, and it's also the statement that we generalize. So, this is, what is superrigidity? Superrigidity is some sort of very weak criterion for extending representations from gamma to H. And now I'm going to proceed to start abbreviating all of my co-authors' names. So our superrigidity theorem says, okay, let's take G SON1. I'm going to stick to this case for now. Let's take gamma in G a lattice. And we're going to look at rho from gamma to H exactly as above. So it should be Zariski dense unbounded image where H is a simple algebraic over some local field. And we have to add some assumptions. And one of them I'm not going to state precisely in this lecture is that H is not too big in square quotes and not in scare quotes. The word we use in the paper, which is absolutely terrible, is compatible. We had a long fight over what this word should be called, and the four of us couldn't agree on a better word, and it's a terrible word we've now put in the literature. So maybe someone should eventually use our work and give it a better name. And these you shouldn't worry about. Now, why shouldn't you worry about them? All I care about superrigidity for here is to prove arithmeticity. All the representations I have to care about to do that satisfy this assumption, and the proof of that is not too hard. But now we need a real big assumption, and there exists a gamma equivariant measurable map from G mod W to H mod L, where W will be SOK1 for some K between 1 and N strictly, and L is just a proper algebraic subgroup. And if I have that map, then rho extends. And maybe I should say a little bit about what this map is. You can think of G mod W as, say, the space of k-dimensional, totally geodesic planes in HN. That is formally what it parameterizes. So you have that thing. That thing is an algebraic variety. I have a measurable map from that algebraic variety to some other algebraic variety that respects my dynamics. It's a weird input to assume you have. And the reason why it's sensible to assume you have it is something about history of proofs and ideas. And so what I want to do now is explain why this was a sensible thing to look for, and then explain how we found it, more or less in reference to Margulis's work. So let's
I guess this is how you're going to encode the existence of totally geodesic subspaces.
Right. So that this map, let's give it a name. We give it a name, yes. We'll be calling it F eventually. And that, sort of the fact is that F comes from the existence of infinitely many maximal totally geodesic subspaces. It turns out that the existence of F is formally weaker than that, but we build it using that, and so far I have no idea how to ever build it not using that. So you can think of F as some artifact of having the totally geodesic subspaces, and maybe it's interesting to try and figure out how to use it without how to build such a map without having infinitely many totally geodesic subspaces. But sort of the end of my talk, I will tell you how to build F in our context, or at least in a special case of our context. But first, I want to make the whole world seem sensible by talking about Margulis's proof very briefly and cartoonishly. There are two steps. One is to build a very similar looking map, which I will also call F by abuse of notation. Our F is the child of his F. This is measurable and gamma equivariant. Where
That's
P is
still a
now,
W? Oh, P. Okay, okay.
that's now a P, sorry. P is now a minimal parabolic. So it's a very different subgroup. W is some simple subgroup. P is some amenable parabolic subgroup. And again, L is the same. L is just proper algebraic. And I'm already lying to you a bit. Saying this way is probably more Zimmer's variant of Margulis's proof than Margulis's original proof. But so it goes, and step 2 is use centralizers of elements of gamma to show, maybe really elements of G to show F is rational. And once you have that this is a rational map, it's falling downhill from there. It's a very trivial exercise to show that if this is a rational map, this map is G equivariant. And if it's a G equivariant map, there has to be some extension of the representation to G. But the key fact here is that he's using centralizers of elements. And for us, somehow I'm going to think of this as a proof of arithmeticity rather than superrigidity. So step 1 is to build the map G mod W to H mod L from the theorem. We've sort of moved step 1 of Margulis's proof into our hypotheses, because it's less natural than his. I should perhaps say that Margulis's step 1 is universal. It does not use higher rank. This measurable map where this is a P, that always exists. It's just a consequence of amenability that I'm going to tell you why it's true in a second. The existence of this map is very non-trivial. And so we've moved the existence of the map sort of out of the proof of the theorem and into the statement of the theorem. And step 2 is somehow more similar, perhaps, to Margulis's arguments. We use properties. It's not very similar, but we use properties of F to extend rho without actually proving that F is a rational map. We use normalizers instead of centralizers. In rank 1 groups, trying to use centralizers is a fool's errand. There just are not many elements in rank 1 groups that commute with one another. And so you don't want to use, centralizers, you want to use something else. And it turns out what works is normalizers. And the other thing I should say here is, there's some sort of input from work Uri Botter had done with Alex Furman. They rewrote the proof of Margulis's superrigidity theorem in somewhat different language. I had the nth iterate of the conversation with Margulis on Saturday about whether their proof was different than his proof. And their proof is much simpler than his proof. But if you have the standards of originality that are Margulis's, it is a simplification and clarification rather than a different proof. I don't know that we should all worry about such things too much, but if you're Margulis, you're allowed to. So let's just take today I'm only going to talk about step 1, in part because introducing all the machinery from Botter and Furman to talk about step 2 is its own errand that would take, a third part of the lecture. And I want to talk about step 1 because, perhaps because I've most often talked about step 2. And so we're going to first do this in Margulis's case, just so I can show you an argument that's comprehensible maybe and not that hard, where I don't have to use very much. When we go to prove our version of it, you have to use a lot. So we have this map rho from gamma into H, and we just pick a vector space V, vector space on which H acts irreducibly. This is a relatively easy thing to do, so I'm not going to talk about it. If it's S ln R, you just act on Rn. If H is S ln R, just act on Rn. That's the representation I want. And then I'm going to look at a space. And the space is going to be what I get by taking G cross P of the projective space on V. I'm going to mod out somehow by the gamma action. And how I mod out by the gamma action is I look at pairs that are G and equivalence classes of vectors. And I want to act on them by gamma on the right and G on the left. And there's sort of only one thing you can sensibly write down here, which is this. I act on the vector by gamma. I act on the group coordinate by G on the left and gamma on the right. And everyone always tells me I screw up which one I have the inverse on. I think it's right, but that probably means it's wrong. And this thing is naturally a bundle over G mod gamma. And there's naturally a G action both here and here. And this map is equivariant. And so this is a nice object. And this is called a suspension or an induced action. Depending, it's an induced action if you're talking to people in sort of representation theory, and it's a suspension if you're talking to people in dynamics. And then, the key step, in fact, the only sort of non-trivial step, which in this case is also trivial, is find a p-invariant measure on this space that projects to har on G mod gamma. And I'll tell you the idea of how you do that, because it's really a line. P is amenable. So averaging produces invariant measures. And so I can find a p invariant measure. There's no cost. You might worry about, well, you added this side condition that it should project to G mod har measure on G mod gamma. And to guarantee the projection, there's a trivial trick. Is that average in measures that project to har. You don't need to use anything fancy. You just look at the class of measures that project down to har measure. That class of measures is clearly p invariant because har measure on G mod gamma is p invariant. And you look, and that means you can do your averaging and get your invariant measure. If you wanted to be fancy instead, you could use the fact that it is a theorem, I think this in this case due to Dani, that all p invariant measures on G mod gamma are in fact har. You could use that. You don't have to. But there is homogeneous dynamics you could use in place of this trivial argument. But why would you do that? Well, we'll do something like it later because it will help us. And once you have this invariant measure, you should be wondering, okay, he's built an invariant measure on a space, and from that he claims he gets a measurable map. And if you haven't, if you haven't seen this before, you have no idea why this map comes from that invariant measure. So I'm going to sketch that very quickly. And so the point is that if you just disintegrate your measures, if I have a measure on this bundle here, then I can say, okay, over each point in the base, I have a measure on the fiber. And that gives me a map that I can think of as a map from G to measures on this projective space. And this is gamma equivariant and P invariant. And you then do some stuff. And you determine that this map G, I'm calling it phi, actually lands in H mod L. Or what is H mod L here? Well, H is acting on the projective, H acts on the vector space, so it acts on the projective space, so it acts on measures on the projective space. And this H mod L you can just think of as the H orbit of the image of some particular point in G. I almost wrote the identity there because everything's measurable. You don't want me to write the identity there because everything might be bad at any individual point. It's only good at almost every point. And this arrow is, maybe it should have names like Furstenberg and Zimmer attached to it. Because again, this is some sort of later reinterpretation of Margulis's original proof. So this isn't entirely trivial. And then, this map is still gamma equivariant, and don't know why I can't avoid doing that. Gamma equivariant and P invariant. This map is still gamma equivariant and P invariant, so we just drop the P invariant map to G mod P, and that gives us F. That's measurable and gamma equivariant. So then it's almost a complete argument. There are some tricky things. Why do I land in a single orbit? Why does my orbit have stabilizer that's an algebraic subgroup? Those are things that require work. But if you're familiar with this area, there are things that there are by now many ways to do. So now what I want to talk about instead is step one. I'll BFMS. And this just becomes much more involved. And I should, there's some sort of inspiration here that I like to credit. From a paper of Eskin, Philippe, and Wright about Teichmuller dynamics. They do something similar in a very, very different setting. It's a setting where there are known analogies, but it's a different setting. So what do we need to do? Sort of by the same type of argument, it suffices to find a W invariant measure on the same kind of space. Immediate problem, W is not amenable. A priori, there are no W invariant measures on this space, let alone, again, we also want mu to project to Haar measure. I haven't really told you why this is essential that mu projects to Haar measure. But let me just flip back up here to tell you in this map why it's important that it projects to higher measure. If the measure that you build doesn't project to higher measure, you don't really have a measure from G mod P. You have a measurable map from some funny measure on G mod P that might not have full support. It might be supported on some fractal subset. And if you try to analyze such a thing, you have sort of lost the structure of this source space being an algebraic variety. You just on some random measure space. And why you want that original measure, the measure you build to project to HAR, is because you want to have the structure of this space available to you when you start making arguments at the second step. So it's absolutely crucial, but I'm not actually going to completely tell you why. So we want to build this measure that projects to HAR measure on this space that's invariant under this group W, but a priori no such measures exist. And in fact, you can deduce from our work a classification of such invariant measures in the context we're working in. And among the things that you can deduce is that if the lattice is not arithmetic, there are no such measures. Or rather, if the representation from gamma to H does not extend, there are no such measures. There are absolutely none. So somehow the existence of the measure seems to be intimately tied to arithmeticity in a way that I don't completely understand yet. And so we want to do the same thing-ish, but now it becomes incredibly complicated. So what I'm going to give you is a recipe. I'm going to give you sort of the things one needs to do to build the measure rather than a complete argument. The thing for Margulis was a complete argument. So the recipe is first, and let's before I start my recipe, let's restrict to G equals SON1 and W equaling SON minus 1, 1. And if I restrict to that case, this is totally geodesic submanifolds of codimension 1 is essentially a restriction here. Some of the lies I tell you will be less lies. They'll very much lies in the general case and not really lies in this case. So what's the recipe? First step is each maximal totally geodesic submanifold N, let's say Ni, there are infinitely many of them, and M corresponds to a closed W orbit in G mod gamma, supporting a W invariant W ergodic measure. The W orbit is, it's W orbit of some G I, which is naturally isomorphic to W mod gamma intersected with GI W, GI inverse up to, again, my having the inverse on the wrong side. And, this is, let's call the measure mu I, and mu I is really just HAR on this orbit. So it's HAR measure on a proper subgroup sitting in, with an orbit sitting inside your big space. The second step, where I'm just going to hide from you a tremendous amount of machinery, or rather make an assertion based on a tremendous amount of machinery that says, we now have infinitely many. I'll say this first step is relatively easy. It's, sort of just translation between geometry and dynamics. And the second step is not relatively easy, but it's mostly other people's work. It's that infinitely many Ni gives you infinitely many mu I, and using really all of the work of Marina Ratner and Shahar Moses should not flip the first names, and Nimish Shaw. We see that these mu I converge weak star to mu, which is Haar measure on G mod gamma. I will say that from the point of view of people doing homogeneous dynamics, this is, 25-year-old technology that compared to what they use now is not so hard, but it uses enough of Ratner's theorem that, it's deeply non-trivial. We're using a tool here or a hammer here that, is serious. The thing I haven't actually managed to find time to think through is, well, I only need Ratner's theorem for certain homogeneous spaces and certain subgroups, and maybe it's a little easier, but it's not, there's sort of an easiest case of Ratner's theorem that was written down by Manfred Einsiedler, where you classify measures invariant under simple subgroups. And you might think we could get away with Einsiedler's simple argument, but because we want a limit of measures statement, that's not true. This is some sort of equidistribution statement that therefore requires more of the machine. And so maybe you can get away with less than the full brutal proof of Ratner's theorem, of which I still don't know a simple account, but you still need most of it. You need it's a big thing I'm hiding. The third thing we use, which is just some sort of consequence of our assumptions. I already said that we have that GI W GI inverse intersect gamma sitting in GI W GI inverse, or I should have said this, and maybe I said it wrong, is a lattice. These orbits being closed means I have smaller lattices floating around. And then what we do is something that I've sort of hidden. We already at the beginning, we constructed some representation of H on V. And we do this so that, let's call this group gamma sub I, leaves a line invariant. And I'm not going to tell you why I can do that in any depth, but it comes from two things. It comes from the fact that this is a lattice in a smaller subgroup, and all of these smaller subgroups in which I'm getting each of these lattices are conjugate. And so, I really need to check this for one gamma I, and then I have it for all the conjugates. That part's easy. But it also uses, there's this representation from rho from gamma into H. And this construction absolutely does not work if I give you an arbitrary rho. We use the fact that all I'm trying to do is use my superrigidity theorem to prove my arithmeticity theorem, and that tells me exactly which rows I need to look at. And there's enough algebraic structure to the rows I need to look at that this becomes relatively easy using not that much machinery and sort of standard styles of argument. But there's some insight required in noticing this is what you want. But once you know this is what you want, it's not so hard to build it. And what this this means just by sort of translation is that there's a invariant line bundle over each closed W orbit which is the same thing as saying over this WGI orbit, we have a section of my bundle. So get a section S sub I. Oh, sorry, my mess up somehow there's lag. I complained before we started about the fact that the iPad talks to the router in the kitchen and then talks to the computer, and this is why it's a problem. Yes, there you go. There's my SI that I wrote 30 seconds ago. So we get a section of this bundle, but only over this orbit. But what we can then do, and then we can just push SI star UI is now a measure on G cross P of V mod gamma. And it stays W invariant because my section was W invariant, in fact. So you're just sort of lifting the measure from this homogeneous space where you know it exists to this space where you didn't know it existed. Maybe we should give it a name when we put it up on the space we want it on. That's new I. And now you just take the W star limit of the new I, call that new, and this is a W invariant measure on this space that by step 2 projects to har. I mean, somehow I'm using some relatively trivial thing here that if I take some measures and I push them up onto this space and I take their weak star limit and I project it back down, the projection of the weak star limit is the weak star limit of the projection. And so it just projects down to the measure you want, and you've completed your construction by using all of this heavy machinery from these other people about homogeneous dynamics. And I think that's all I wanted to say about proofs today.
Okay, so let's all unmute and thank David very much for the beautiful lectures. Thank you.
Thank you.
We have time for some questions and discussion.
I would like to ask about this bundle, I mean, G product POV, and is it originally motivated by which papers? It comes from Margulis, right? Or first?
It comes from, I mean, in this context, it's definitely Margulis's, but it's you know, it's an older construction in dynamics. Definitely, I mean, you know, hopefully we don't get back there. You know, at the time, it was certainly present in work of Mackey's that was older than Margulis's work. I don't think Margulis was aware of the work of Mackey that preceded this. I think he just came up with this construction based on the you know, there's a standard dynamical systems notion of the flow under a function, and this is some not so profound generalization of that to the action of a bigger group. And Margulis, certainly, you know, educated in the Russian school of dynamics at the time, knew all about flows under a function. He was just, you know, saying, oh, I can do this too. The other thing it sort of resonates, which was I don't think he was thinking about, is it sort of resonates nicely with flat bundles, but he was definitely coming from a dynamical point of view. So
I see it's like a general approach, right? To consider some bundles, to project down, or to lift measures, right?
So it certainly is a general approach to consider these bundles. This construction of induced action appears sort of everywhere in the subject, where the subject should be now the most broadly defined version of it, I guess, because, you know, it appears in homogeneous dynamics, it appears in, you know, this rigidity stuff, it appears in all the work on the Zimmer program, and it just, you know, yeah, it's a standard thing. And the main reason why it's useful, right, is that if you start with a lattice gamma, you know, unless you start with a very special kind of arithmetic lattice, you know nothing about the algebraic structure. And G, on the other hand, has tremendous algebraic structure that we've known what it was since Cartan, and it's very useful and easy to manipulate. And so there's really what the induction structure lets you do, and bringing it to the study of lattices is definitely Margulis's idea. Is you know you can try and, you know, build by hand the arithmetic structure on gamma, but that's very hard. And so instead, you put yourself in a situation where you can exploit the arithmetic the algebraic structure that already exists on G. And I think that philosophically is what it's for, and why he invented it.
I see, thanks.
So this question about SO41, trying to find a non-arithmetic, or trying to find a lattice that has no sort of codimension 1 subplane. Like, so in hyperbolic 3 space, I guess the Thurston work you're referring to is not complements and the like, right? You can construct all these, and a lot of them. So Alan Reed tells us only the figure 8 complement is arithmetic, if I recall.
Right, only the figure 8 not complement is arithmetic, and you can easily from that build lots of examples that, you know, aren't arithmetic, co-compact, not co-compact, your choice. You know, they're just scads of them, but the only way we know how to build them is hyperbolic Dane surgery, which, you know, you can do things in higher dimensions with people call hyperbolic Dane surgery, but none of them build hyperbolic manifolds. You know, you can follow Anderson and build Einstein manifolds, or you can follow whether, I don't know whether you want to say Fujiwara, Manning, or Ocean. I think there's some conflict there, and do it in sort of a geometric group theory context and build hyperbolic groups this way, but you can't build hyperbolic manifolds this way. And that's essentially a theorem that you can't build hyperbolic manifolds this way.
How do you prove that in these Thurston constructions you will not have these you know, subspaces, these totally geodesic?
So there you get lucky, and it becomes an algebraically checkable condition, right? You build your manifold, and it has a trace field. It also has a quaternion algebra. But if the trace field has no totally real subfields, then you have no totally geodesic submanifolds. Okay. And what these guys know is they know well enough to how to, you know, you do Dane surgery, they know how the trace field changes. Which isn't obvious, but it's, you know, by now it's ancient technology. You know, you do Dane surgery, they know what happens to the trace field, and then you just check. It's not
and
so
that
hard.
Doesn't work in 4 space. Well, first of all, we need some constructions in hyperbolic 4 space.
Yeah, but then
it's not just a matter of the trace field there.
Yeah, I mean, I've thought about this on and off, but, you know, there's just nowhere to start in terms of making it a trace field condition.
Because it's SO21 inside SO31 as opposed to now SO31 inside SO41.
Right,
and you know, control the
right. And first, you want to talk about adjoint trace fields, because trace fields are not a good idea in higher dimensions, and then it's just, you know, what about a trace field tells you something about, you know, a subquadratic form? It really, you know, the other argument depends very heavily on the fact that you can, you know, use these exceptional isogenies to say you're an SL2R and SL2C instead of SO21 and SO31.
Yeah, very interesting. Misha Belolibetsky, I see. Did you want to say something? Oh, no. Okay.
Just thinking about trace fields. We have some things about adjoint trace fields in our paper, not directly related to a question. So,
yeah, no, if you can come up with a condition in terms of adjoint trace fields, you know, it at least gives us a target. You know, when you start trying to make a construction, if you then don't know how to prove anything about it, it's not helpful. And I can say a little bit, you know, the construction we started with was just trying to do some version of Gromov, Piatetsky, Shapiro along manifolds with corners, and we can do something, but there's a problem with this, in that, you know, maybe you can do something really complicated that we can't currently do, and do some cut and paste construction where you don't automatically build yourself a totally geodesic submanifold. We can't do that, but we've tried on and off, and maybe you could do that. But in order to do any of these constructions, you pass to some large cover to get everything to, you know, cut right and be embedded right and intersect right. And you know, Misha knows more about that than I do. And then you're trying to glue, and so maybe you can get the gluing locus not to give you a totally geodesic thing, but you've passed all these covers, and probably you've put billions of totally geodesic manifolds elsewhere in your manifold, unless you have some way to control that. And having a trace field condition might give you a magic trick to control that, not quite explicitly, because I don't think you're going to control it explicitly by construction. It's just too much to ask. You need some sort of, you know, implicit way of controlling it that I can't think of.
Any further questions or comments? Well, if not, we can all unmute, and let's thank David one more time for the beautiful lectures. Thank you so much, David.
Thank you very much.
Yes, I greatly enjoyed being on your speaker list between Koncevich and Kajdan. Just not a bad
Well,
place to be.
We were delighted that you were able to do it. So thank you so much.
You
Thank-
were able to give this talk. Yeah, thank you.
Okay,
Thank
thank
you.
you all. Bye bye.
Okay. Thanks all.
Bye all.
See you next time.